In the fourth part of this video lecture, we're going to continue in the proof of the theorem which says the existence and uniqueness of a product measure. And this theorem, it asserts existence of a function that to each set E assigns a non-negative number in a way that it is a measure. And moreover, that we can compute it by this method. And by computing it by this method, we get a function with this property. And let's move to the proof. We already discussed what is it that we have to prove. We already have uniqueness. So we just have to show two things. First, that this process that assigns to each measurable set E a number, that it is a measure. And moreover, when the set E happens to be a rectangle, this measure will be given by the product of the measures of the side of that rectangle. So the first question we should ask is, can we integrate this? The answer is yes, we can integrate this because this as a function of x is measurable. This is what the lemma, let us go back there, the lemma at the beginning of this video lecture, it was saying that this function here is measurable. So now this is measurable, so it can be integrated because it's measurable and non-negative. Okay, we define this function, and let's call this function the mu ball product nu sub index 1. We have not yet shown that it is a measure, but we are very optimistic, so we're already using this notation for it. And we're going to do something similar by fixing y, taking the cross-section, measuring the cross-section, integrating with respect to y, and we're going to call this function mu cross nu sub index 2. And we're going to see what these measures give. Well, in fact, we can look only at the first one. Everything we show for the first one will hold symmetrically to the second one. So let's check that this function is a measure. To do that, well, we do check three things. First one, if it's the empty set. So what does it mean to integrate the empty set? Well, we take the cross-section. The cross-section of the empty set is empty. So in the measure of the empty is 0. So we're integrating the function which is constant equal to 0. We get 0. Check. This is the first property of a measure. Second property of a measure is being sigma additive. So we take disjoint sets of F2 and we want to apply countable additivity of the second measure. How do we do that? Well, we want to compute this function, which is given by definition, is given by this integral. And we know what is the section. This is the section of a union. We have already shown this in the first video lecture, that this is the union of the sections and that they are disjoint because the section of the intersection is also equal to the intersection of the sections. And now, because these are disjoint, and nu is a measure, so it is sigma additive, so this becomes a sum of the measures of EI section. And because the integral is an operator which is also sigma additive, then the integral also goes out here, the sum also goes out here. And this is the definition of the measure mu cross nu sub index 1 evaluated at these sets EI here. And this is exactly what we had to show. So we just showed this is sigma additive if we compare these two. So we have checked also the second property. So yes, mu cross nu is a measure. So there's only one box missing to tick, which is to show what mu cross nu gives for a rectangle. Well, but that we have also seen in the previous proof, in the proof of the previous lemma, this formula here. And when we integrate now this formula, this is we integrate it with where x is the variable. This becomes just a constant, a non-negative constant, possibly infinite. It's no problem. So what will be this, by definition, of this function that we are defining on the rectangle A times B? This will be by definition, this will be the integral of the measure nu of the section A cross B at x, and then we integrate it with respect to the variable x. But now when we substitute, using this identity, we substitute, this becomes nu of B, indicator A of x. Now, nu of B is just a constant, so we can integrate inside. And this is just mu of A. This integral is just mu of A. So we have proved that this function that we defined, it gives what we want once the set is a rectangle. Well, analogously, the very same proof, just switching x by y, etc., will give us the same formula for the second integral that we can compute. And this concludes the very long proof of the theorem of existence and uniqueness of product measures. This concludes this very long and consuming video lecture.